Welcome back to the Deep Dive. Today, we are doing something a little different. We're not just looking at a movie.
No. We're cracking open a physics textbook that just happens to be one of the biggest blockbuster films of the last decade.
We are strapping in with Cooper and Tars, and we're heading straight for Gargantua. We're talking about Interstellar.
It really is the gold standard for hard science fiction. I mean, what Kip Thorne and the Nolans did was pretty revolutionary.
In what way?
Well, they didn't use science to just, solve the plot with some kind of techno-babble.
Right.
They used the fundamental laws of the universe as the antagonist. The bad guy isn't a monster. It's the geometry of space-time.
And nowhere is that more terrifying than on Miller's planet.
Oh, absolutely. That one location, that water world, it sets up the entire film's stakes based on one staggering physical constant.
That time dilation.
That one line. 1 hour here is 7 years on Earth.
7 years. For every single hour you spend on that surface. I mean, if you do the math,
yeah,
7 years is about 61,320 hours.
So that's your time dilation factor. We're talking about gamma, the Lorentz factor, being roughly 61,320 to 1.
And that number, that one number, is basically the mission statement for this whole deep dive, right?
And it is. Our goal is to deconstruct how Kip Thorne took that narratively essential, frankly insane number and prove that it could be, mathematically possible under the rules of general relativity.
Because it's not just one problem. That one number creates, 4 huge physics challenges?
At least. You've got to figure out the black hole itself. What kind of object is it?
Then you have to figure out how the planet can even orbit there without falling in. That's the stability question.
Then there's the Roche limit. How does it not get torn to shreds by tidal forces?
And finally, the big one, visually. Where do those kilometer-high waves come from?
Exactly. And we have to start by talking about the backlash.
Oh, right. When the film came out, people were not buying it.
No, you had established physicists, astronomers, science communicators. A lot of them lined up to say, this is impossible. And, their arguments were based on good, solid physics.
But they were incomplete.
They were working with an incomplete model. And that's what we're going to show you. Why those initial critiques were mathematically sound, but ultimately incorrect.
Okay, so let's put ourselves in their shoes.
Yeah.
A physicist in 2014. What are the two big, immediate, show-stopping problems with Miller's planet?
The first one, the one everyone jumped on, is orbital stability. It's what's called the ISCO problem.
ISCO standing for the innermost stable circular orbit.
Exactly.
So can you break that down? What is the ISCO, really? Not just as a line, but as a physical consequence.
Sure. Think about orbiting something normal, like Earth. The closer you get, the faster you have to go to stay in orbit, right? To fight gravity.
Standard orbital mechanics.
Right. But near a black hole, space-time itself gets so warped that the gravitational pull increases at this terrifying nonlinear rate.
It's not a smooth curve anymore.
Not at all. And eventually, you hit a point of no return. A point where, even if you were moving at the speed of light, the curvature of space itself would pull you in faster than you could escape sideways.
That's the ISCO.
That's the ISCO. It's the universe's final checkpoint. You cross it, you're done, you are spiraling into the singularity. There's no engine, no maneuver that can save you.
Okay, so it's a hard physical boundary. Now let's apply the standard model of a black hole to that.
The simplest model we have is the Schwarzschild metric. Carl Schwarzschild figured it out in 1916.
And the key assumption there?
The black hole is static. It's not spinning. It's just a point of mass.
So for a simple non-spinning black hole, where is the ISCO?
It's at a very specific, very firm location, 3 times the Schwarzschild radius. So 3 Schwarzschilds, that's your closest stable parking spot, period.
Okay, 3 times the radius. So let's put our planet right on that razor's edge. What's the absolute best time dilation you can get at the ISCO of a Schwarzschild black hole?
Well, the math is pretty restrictive. You run the numbers for an orbit at exactly 3 Arcillars, and the maximum time dilation factor you get is about 1.22.
1.2, not 60,000.
Not even close. 1.22 means 1 hour on Miller's planet would be, about 73 minutes on Earth?
So that was the core of the first critique. It seems like a slam dunk.
It did. The argument was, look, to get 60,000x dilation, you need to be practically skimming the event horizon at $1, but the stable limit is at 3 Arcillars.
The planet would have to be orbiting deep inside the unstable region.
Massively inside. The conclusion was simple. That orbit is impossible. The planet would have plunged into Gargantua millions of years before the Ranger ever got there.
Okay, that seems pretty damning, but that's only problem number 1. What was the second big roadblock?
The second was about the planet itself, its structural integrity, the Roche limit violation.
Tidal forces.
Tidal forces. Basically, the Roche limit is the distance where the difference in gravitational pull across an object is stronger than the object's own gravity holding it together.
We see this with comets getting too close to Jupiter. They get torn apart and form rings.
Exactly. It's spaghettification, but for a whole planet.
And the critics' argument was that to get that 60,000x time dilation, you're so close to the black hole.
That the tidal stress would be unimaginable. The side of the planet closer to the black hole would be pulled so much more forcefully than the far side that the planet would just be stretched and shredded into a stream of hot gas.
And that intuition comes from thinking about normal-sized black holes, right?
Absolutely. If you're near a stellar mass black hole, say 10 times the mass of our sun, the event horizon is only 30 kilometers across. The gravity changes so steeply over that distance that you would be ripped apart long before you got there.
So the critics just applied that same logic to Gargantua.
And why wouldn't you? On the surface, it makes perfect sense. So you have two killer arguments. The orbit's unstable, and even if it weren't, the planet would be destroyed.
And yet, here we are. So both of these critiques share a fatal flaw.
They do. They're both perfectly correct, perfectly sound, if you assume Gargantua is a non-spinning Schwarzschild black hole.
But it isn't.
And that's the whole key. Kip Thorne's solution was to say Gargantua isn't static, it's a rapidly spinning Kerr black hole. And that spin doesn't just tweak the math, it fundamentally rewrites the rules of spacetime.
Okay, so this is where we leave the simple model behind and dive into the really weird stuff.
This is where we characterize Gargantua.
To make this all work, Kip Thorne didn't just say it's spinning. He gave Gargantua two very specific, very necessary properties. Let's start with the first one, its size.
It's super massive, just enormous. Thorne set its mass at 188 solar masses. That's 100 million times the mass of our sun.
And that number isn't just to make it sound impressive, it's actually a safety mechanism.
It's the first crucial safety mechanism.
Which seems totally backward. You'd think a bigger black hole would be more dangerous, not less.
And this is one of those great counterintuitive things about general relativity. It all comes down to the scale of the event horizon. For a black hole that massive, the Schwarzschild radius is about 300 million kilometers.
2 astronomical units.
2 AU. The event horizon itself is roughly the size of the orbit of Mars. It's colossal.
You're not falling into a point, you're falling into a region of space bigger than our inner solar system.
Exactly, and that scale is what leads to what we can call the tidal paradox. Because tidal forces, the stretching forces, are actually inversely proportional to the square of the black hole's mass.
Hang on. The bigger it is, the weaker the stretching force is at the horizon. Why?
Because the gradient is shallower. Think of it like a hill. A stellar mass black hole is like a tiny, incredibly steep cone. The slope changes dramatically over just a few feet. A supermassive black hole is like a mountain the size of a continent. It's immensely tall, but the slope you're standing on is very, very gentle.
So the difference in gravity between your head and your feet, or one side of a planet and the other, is much smaller.
Much, much smaller. So the supermassive size is what saves the planet from being instantly spaghettified.
Okay, that solves the Roche limit problem, but it doesn't solve the stability problem. For that, you need the spin.
For that, you need the Kerr metric. Roy Kerr figured this out in 1963. It's the solution to Einstein's equations for a spinning mass. It takes into account angular momentum, Jay.
And the math is notoriously brutal. But what's the one key physical idea that the Kerr metric introduces?
It's an extra term in the metric, an off-diagonal term, the D and TD fight away.
Which, in plain English, means?
It means that time and rotation are coupled. They're linked. The spinning mass doesn't just sit in space-time, it actively drags space-time around with it.
This is frame dragging.
This is frame dragging, or the lens stirring effect. Kip Thorne calls it the space whirl.
It's like a spoon stirring honey. The honey right next to the spoon gets dragged along for the ride.
That's a perfect analogy. The planet isn't just orbiting a static gravitational well anymore. It's caught in a whirlpool of moving space.
And that whirlpool provides a kind of lift.
It provides a powerful centrifugal force, as long as you're orbiting in the same direction as the spin of prograde orbit. That space whirl is actively pushing you outward, helping you fight against gravity.
It's the secret ingredient for stability. And we measure how fast it's spinning with a specific parameter.
The dimensionless spin parameter. It goes from 0 for a non-spinning Schwarzschild black hole up to 1 for a maximally spinning or extremal Kerr black hole.
The laws of physics sort of forbid anything spinning faster than $1 because it would create
a naked singularity, which most physicists think is impossible. It's called the cosmic censorship hypothesis.
So let's connect that spin back to the ISCO. How does frame dragging change the location of that innermost stable circular orbit?
Well, remember, for a non-spinner, the ISCO was way out at 3 Arbalers.
Right.
As you spin the black hole up, that centrifugal support from the frame dragging gets stronger and stronger. It allows you to get closer and closer while still being stable.
The faster it spins, the closer you can safely get.
And as that spin parameter gets very, very close to 1, something amazing happens. The ISCO moves all the way in until it basically merges with the event horizon itself at $1.
So the cliff of instability is gone.
It's gone. For a near maximally spinning black hole, it becomes a stable shelf. You can, in theory, orbit stably right on the edge of the abyss.
And if you can orbit there, you are in the deepest part of the gravity well possible.
Which means the time dilation can become arbitrarily large. It can approach infinity.
And that is how Miller's planet is possible.
That's the framework. But now we need the exact numbers.
Right, this is where it stops being theoretical and becomes an engineering problem. We need that factor of 61,320. So the question Kip Thorne had to answer was, how fast exactly does Gargantua need to be spinning?
He had to do the calculation in reverse. He started with the answer, the time dilation, and solved the Kerr metric for the spin.
Okay, what is the number? What is the required spin parameter, Egal?
The value he calculated to make the film's plot work is that Gargantua must be in a near-extremal state. The spin parameter is approximately 1 minus 1.3 times 10 to the minus 14.
Wait, say that again?
1 minus 1.3 times 10 to the negative 14.
Yeah, that's 0.999 with 13 nines, and then an 87 at the end.
Pretty much. It means Gargantua is spinning at 99.99999999999% of the absolute maximum speed allowed by the laws of physics.
That is just staggering. It can't spin any faster without breaking the universe.
It's right on the hairy edge of cosmic censorship. It's a statement that says, for this story to work, this black hole has to be the most extreme object of its kind that could possibly exist.
Let's talk about how likely that is. I mean, astrophysically, do we think black holes can even get that close to maximal spin?
Probably not. Most models suggest there's a practical limit, the Thorne limit actually, which is around a 0.998, because black holes grow by eating stuff, right? Accretion disks. And not everything in the disk is spinning the same way. Some material will fall in with a retrograde spin, acting like a brake.
So to get to Thorne's number for Gargantua, it would have had to have been fed a diet of only perfectly prograde material for its entire life.
With incredible precision. So, is it astrophysically likely? Almost certainly not. Is it mathematically valid according to Einstein's equations?
Yes, it's the ultimate edge case. And that extreme spin dictates exactly where the planet has to be.
It has to be, as the movie says, just a pinch from the event horizon. Thorne's calculation puts the orbital radius at about 1.00003766 times the black hole's mass.
It's literally hovering just fractions of a percentage point outside the point of no return.
And its stability is entirely dependent on that spin staying constant to 14 decimal places. If Gargantua swallowed one asteroid going the wrong way, the spin would slow just a tiny bit.
The ISCO would move outward.
And Miller's planet would be gone. Instantly.
So when they're flying down in the Ranger, they're moving incredibly fast relative to the people on the Endurance.
Oh, yeah. Relative to a distant observer, the planet itself is whipping around Gargantua at about 55% of the speed of light.
But locally, it's stable.
Because the frame dragging is carrying it along, its speed relative to the swirling space around it is much lower, and it completes one full orbit around this enormous 2 AU radius black hole in just 1.7 hours of coordinate time.
So someone on the Endurance would see the planet do a full lap in under 2 hours.
But for the people on the surface, that same lap would feel like it took 7 years relative to Earth.
That's just mind-bending.
It's the beauty of the Kerr metric. It shows you how deep the rabbit hole of time can go if you push the physics to its absolute limit.
Okay, so extreme spin solves stability. But let's go back to that other problem, the Roche limit.
Right.
Even if the tidal forces are gentler because it's supermassive, they're still the tidal forces of a 100 million solar mass black hole. How is the planet not just stretched into a football shape and torn apart?
Well, the first line of defense, like we said, is that on M22 scaling, that huge 2 AU horizon really does flatten the gravitational slope.
But gentle in this context is still, immense by our standards.
Oh, absolutely. The planet still needs a way to fight back. It needs incredibly strong internal gravity to hold itself together.
Which means it needs to be incredibly dense.
Exactly. So Thorne did the math on that too. He calculated the bulk density the planet would need to have to resist being torn apart in that specific orbit.
And what's the number?
Miller's planet has to have an average density of roughly 10,000 kilograms per cubic meter.
10,000. Let's put that in perspective. What's Earth's density?
Earth is about 5,500. So Miller's planet needs to be almost twice as dense as Earth.
What's that even made of? I mean, iron is only about 1,700.
You're talking about a world made of super heavy elements. Its core would have to be absolutely massive and composed of things like osmium, which is the densest stable element we know of, or uranium, gold, platinum.
It's a cannonball made of precious metals with a thin layer of water on top.
That's a pretty good picture. That immense density is what provides the internal gravity needed to resist Gargantua's pull. It's the planet's personal defense mechanism.
And you can kind of see the effects of that stress. The planet is tidally locked, right?
Yeah.
One side always facing the black hole.
Right, which helps stabilize it. But it also means it would be deformed into a prolate ellipsoid, a bit of a football shape, stretched along the axis pointing toward Gargantua.
So the solution is a two-part defense. A supermassive black hole to weaken the tides, and a super dense planet to withstand what's left.
That's the complete picture. And it's so satisfying because it shows why those initial critiques were, well, they were based on a simpler model.
Which brings us to that great story about the retraction. The astronomer Phil Plait was one of the big early critics, right?
He was. He wrote a very popular article basically explaining why the physics was impossible, focusing mostly on the ISQ problem.
But then,
after Thorne and others published the detailed papers explaining the math behind the Kerr solution, Plait did something amazing for a science communicator.
he admitted he was wrong.
He publicly retracted his critique. He wrote a follow-up piece called My Mea Culpa and explained that his analysis was based on a non-spinning black hole. He hadn't accounted for the extreme frame dragging.
And he confirmed that with a near-extremal Kerr black hole, the math absolutely does work.
It's a fantastic moment for science communication. It shows how counterintuitive this stuff is. You need the full picture of general relativity, or you'll get the wrong answer.
Okay, so the planet is stable, it's holding together. Now we have to talk about the most iconic feature, those waves.
The giant waves.
We have kilometer-high, 4,000-foot walls of water on a planet where the crew says the ocean is only knee-deep.
Yeah.
How on earth do you get a wave that's thousands of times taller than the water is deep?
This is where we get into relativistic hydrodynamics, which is a field all on its own.
So let's lay out the parameters. Surface gravity is about 1.3 times Earth's. And the ocean is, what, maybe a meter deep at most?
Yeah. Thorne modeled it as about 0.5 to 1 meter deep. So right away, you know it can't be a normal wave.
No wind on Earth could do that.
Not even close. You can't build a kilometer-high wave in a puddle, so the mechanism has to be gravitational. We're in the realm of the shallow water equations.
Which apply when the wavelength of the disturbance is way, way bigger than the depth of the water.
Exactly. And if you just look at the normal speed of a wave in shallow water, which is the square root of g times h gravity times depth, the wave should be moving pretty slowly.
But what we see isn't a normal wave. It's a single massive wall.
It's a tidal soliton. Solitary wave or a tidal bore. It's not a repeating surface wave. It's a massive displacement of water.
So what's the engine driving that displacement?
The mechanism is called tidal libration. It's basically a gravitational rocking motion.
But wait, I thought the planet was tidally locked. One side is supposed to stay pointed at Gargantua.
It is, on average, but the orbit isn't a perfect circle. It's slightly eccentric. So as the planet moves along its elliptical path, its orientation relative to Gargantua wobbles a tiny bit. The solid crust of the planet is rocking back and forth underneath the ocean.
So the ground is literally shifting under the water.
Precisely. And the ocean, being a fluid, is trying to keep its tidal bulge perfectly aligned with Gargantua's immense gravity.
So the water wants to stay put while the planet rocks underneath it.
And that creates this enormous sloshing effect. But because the ocean is so incredibly shallow, that sloshing energy has nowhere to go. It can't dissipate horizontally.
It has to go up.
It has to go vertical. The nonlinear terms in the shallow water equations take over, and the disturbance steepens into what's called a hydraulic jump or a shock front. All that water just piles up on itself.
And that's how you turn a small rocking motion into a 4,000-foot wall of water.
It's a monstrous soliton that just endlessly circles the planet, chasing that gravitational sweet spot. Thorne's math showed it could absolutely reach heights of 1.2 kilometers.
Which also explains that strange scene when they land.
Mm.
The water is gone. It's just a shallow mud flat.
Exactly. The water has receded. It's been pulled away to feed the approaching soliton. The reason it's knee-deep when they land is because the rest of the ocean is currently in the form of that giant wall of water coming towards them.
It's such a perfect, terrifyingly consistent piece of physics.
It's beautiful, isn't it? It all fits together.
So that covers the physics of the planet. But what about the physics of just seeing it? The visualization was a huge part of this.
A monumental part. I mean, before Interstellar, what did a black hole look like in a movie?
A black circle with a kind of flat, glowing ring around it, like Saturn.
Right, because all standard CGI software is built on one simple assumption. Light travels in straight lines.
But near Gargantua, it absolutely does not.
Not even a little. Light follows the curved geodesics of space-time laid out by the Kerr metric.
So to render it properly, you can't use a normal graphics engine. You need a physics engine.
You do, and they had to build one. Kip Thorne worked directly with the VFX team at Double Negative, a guy named Oliver James in particular, and they wrote custom software to do it.
The double negative gravitational renderer, the DNGR.
Yep. And what this software did was essentially solve Einstein's equations backwards for millions of individual light rays. It would trace their curved paths from the camera back to their source to figure out what the camera should see.
That sounds computationally expensive.
It was pioneering, especially because of the extreme gravitational lensing. A tiny change in a light ray's path near the black hole could make it end up coming from a completely different part of the sky.
You'd get weird sparkling artifacts and noise.
Exactly, aliasing. So they had to develop a new bundle method for ray tracing, tracing whole patches of light rays at once to smooth out the image.
And what's so cool is that by doing this, by just trying to make the movie look right, they ended up creating the first truly accurate visualizations of some key relativistic effects.
They really did. The most famous one, of course, is the Einstein ring, that full halo of light that seems to wrap around the black hole.
It's because we're seeing the back of the accretion disk, right?
We're seeing the top, the bottom, the front, and the back all at the same time. The gravity is so strong that it bends light from the far side of the disk up over the top and down under the bottom of the black hole and sends it towards your eye.
The black hole is acting as a lens for its own disk.
Perfectly put. And the other big thing they visualized correctly was the asymmetry of the disk.
One side is much brighter than the other.
It is, and that's the visual proof of the extreme spin. It's called relativistic Doppler beaming.
The part of the disk spinning towards us is blue shifted and brighter.
And the part spinning away is red shifted and dimmer. The fact that you can see that so clearly is the visual confirmation that Gargantua is indeed a near-extremal Kerr black hole spinning at an incredible rate.
It's amazing that a movie's VFX department ended up publishing peer-reviewed science papers.
2 of them. In journals like Classical and Quantum Gravity, the process of creating the visuals became a legitimate scientific exercise. It showed us, for the first time, what a black hole must look like if general relativity is true.
Okay, so let's try to wrap this all up. We started with what seemed like a scientifically impossible premise.
And we've ended up with a model that, while, let's say, wildly improbable, is completely sound according to the laws of physics.
So let's just recap the key takeaways. First, to get that 61,000x time dilation, you absolutely need a near-extremal Kerr black hole.
That spin has to be precise to 14 decimal places. That's what creates the stable shelf right next to the event horizon.
Second, for the planet to survive there, 2 things have to be true.
Gargantua has to be supermassive, which weakens the tidal forces, and the planet itself has to be super dense, about twice as dense as Earth, to hold itself together.
And third, those unbelievable waves aren't really waves.
They are tidal solitons, giant hydraulic shock fronts caused by the planet rocking back and forth in its slightly eccentric orbit.
It's just a stunning symphony of extreme physics, all working together to justify losing 7 years in an hour.
And the final point to take away is just how fine the margins are. That spin parameter, that value, being so close to 1 tells you that the universe allows for these extreme solutions, but only on a knife's edge.
Which brings us to our final provocative thought for you to think about. The physics of Miller's planet, especially that absurdly unlikely spin rate, is mathematically valid in our 4 dimensions.
Right.
But the film's larger plot relies on beings in higher dimensions, on bulk fields and exotic physics. So here's the question. Could that be a necessary part of the equation? Could it be that for an object to exist and remain stable at the absolute theoretical brink of impossibility?
You need a little help.
Maybe you need some kind of higher dimensional physics, not just to travel between stars, but to stabilize the most extreme objects in the universe.
A stabilizing factor from outside our normal space-time. It's an interesting thought. The universe has these rules and it follows them, but maybe there are other rules we just can't see yet.
Well, on that note, thanks for joining us for this deep dive into the edge of time itself. We'll see you next time.